So this video discusses the background and context for solving nonlinear equations. When we say solving equations or solving nonlinear equations or equations in general, this can be recast almost always into a problem of finding roots of an equation. And with finding roots of an equation, we mean that we want to find arguments x such that a function f is equal to 0. So this means that we want to find the root of an equation or the 0 of the function f, and we will use both terms interchangeably throughout this lecture. Now this might seem quite restrictive, this definition, but virtually all problems of solving equations can be recast into a form that is amenable to solving this function or finding the zeros of this function. Let's take a look at some examples. So first off, we have here a linear equation that we want to solve. So for given constants a and b, we want to find x such that ax plus b is equal to 0. And this also already shows why the focus of this chapter is on nonlinear equations instead of linear equations, is because for linear equations, we can actually solve them relatively easily, at least when there are few equations. So here we have only one equation, and we can simply solve it by moving this b from the left-hand side of the equation to the right-hand side of the equation and dividing everything by a. In that case, we get the following solution: x is equal to minus b over a, which, when plugged into this equation, renders the left-hand side equal to 0. So that's exactly what we want. Also, some nonlinear equations are relatively easily solved. For instance, let's take a look at this equation, a quadratic equation. A x squared plus bx plus c is 0, where again a, b, and c are known constants, and we want to find x such that this quadratic function is equal to 0. We know how to solve this by using our trusted discriminant formula. We know that there are two roots of this equation, and they can be described as follows, as a function of a, b, and c. Now, when looking at this expression for the roots of this nonlinear function, already some kind of issue pops up. We have to evaluate here a square root. Now, if the number that we want to compute the square root for is an easy number, let's say 9, then this is no problem at all, because the square root of 9 is simply equal to 3. However, when we have a non-trivial square root here, for instance, the square root of 2, well, then computing this root by hand becomes a lot less trivial. Well, you can say, well, to compute the square root of 2, I just plug it into my calculator and see what comes out, 1.414, etc. However, how does your calculator compute the square root of 2? That's also kind of a question that needs to be answered. Well, it turns out that actually computing the square root of 2 can also be recast into a form like this, where we have to find the zeros of a function. Well, how do we do this? Well, by simply recognizing that the square root of 2 would be the solution to solving this equation. And note that this is a nonlinear equation, so we have x squared minus 2 is 0. But how do we solve this? So we don't know how to really compute the square root of 2, and well, we can again make this a bit more explicit for x, but then we just get x is equal to square root of 2, and that brings us no step further. So how do we solve equations like this? And that will be what we discuss within these lectures. Another example, let's say that we have some higher order polynomial function that we have to compute the zeros of. Well, now we cannot use formulas like this anymore because there's no general representation of the zeros of such a high degree polynomial. So again, how do we solve such an equation? I don't know. Well, we will know after these lectures, but at this point, that is not trivial at all. Or even slightly more exotic. Let's say we have some trigonometric functions in there, or this could be logarithmic or exponential functions. How do we solve such an equation? So how do we find x such that this equation or this left-hand side is equal to 0? Again, that is not known at this point, but we will discuss that in the following lecture. There are specific cases that can be identified based on properties of the function f. So it's possible that it actually can be the case that there is no solution to this equation f of x is 0. Or in other words, we cannot find an x such that when plugged into f, the outcome will be 0. And this can be easily seen on this graph. There is no x for which the function crosses the x-axis, for which this equation would be fulfilled. Now, it's also possible that there is one and only one solution, as for instance in these two examples over here. But it's also possible that there are actually several solutions in nonlinear equations for which a single function, which is a function of a single variable, is equal to 0. Within 2WN50 and within this video lecture, we will focus mostly on the case where we have one and only one solution. In the textbook, there is a section which also deals with multiple solutions, but that is a optional reading material and is in that part not really part of the course, let's say. Also, we focus on one nonlinear equation f, which is a function of one variable x. Again, in the textbook, there is a section on how to expand this to one function or multiple functions which are dependent on multiple variables, but that again is not part of this course. Let's take a look at an example. So this is an example from geometry where we have a circle with radius r, and then by defining an angle theta, we can take a look at this circle segment and take a look at what the area of this circle segment as defined by this angle theta would be. I'm going to spare you the geometrical details and give you actually the expression of this area as a function of r and theta. And if you want, you can check out how this function is derived, but I'm not going to discuss that in this lecture. Now, we want to solve the following problem. So let's say that given a value for this area and the radius of the circle, we want to find the angle theta that kind of describes this area AS. So given AS and R, we want to find theta. So we can recast that into this form. So we want to solve a nonlinear function of theta. F of theta is 0. And we can see that by using some straightforward manipulation of this equation. So we just bring this guy to the left-hand side. This corresponds to the following. So we have as a function of theta the area minus this term on the right here. And we have given AS and R, in this case 8 square meters and 3 meters, and we want to find the theta that's for this radius of 3 and for this area of 8. We want to find the theta such that this geometrical example holds. Now we can, we can just plug in various values of theta and try to plot the solution. And from this we will see, theta, we plotted it from 1 to 4 here. From this we see that this function seems to have one solution here at theta between 2 and 3. So that gives us a rough indication as to where the root of this equation lies. But we obviously want to be able to compute it within significant accuracy. So we want to compute it, let's say, to 5 significant digits or so. So let's try to plug in some values for theta and see what the value of f is if we plug in that value of theta. So let's say that I make an educated guess. This is somewhere roughly in the middle between 2 and 3. It's a bit to the left, so let's plug in theta is 2.4. Well, and I see that f is quite small here, but it's not 0. So 2.4 is not the solution to this equation, to this nonlinear equation. The function is still positive though, so that means that we have to make theta a bit bigger in order to go closer to this solution over here. And let's try that. So let's plug in 2.43. And indeed, we see that f has become significantly smaller, but it's still non-zero. So we have to go a bit higher theta. Again, how I come to these values, well, that will become clear in the next slides. But we see that by choosing theta ever closer to the actual solution, which is unknown in the reality, we can make f smaller and smaller. And at the actual solution, f of theta will be equal to 0. Now, how do we actually find or refine the value of theta such that we can get f smaller and smaller? And that is basically the topic of this chapter. So solving these equations numerically, well, that basically follows the same scheme or the same approach that I did in the last slide. So from an initial guess, we try to iteratively improve the accuracy based on the knowledge of f that we are achieving through every computation of f at a certain guess. Because we do this iteratively, well, we increase the accuracy as we go through the iterations, but it's very rare that we will actually find exact solutions. So there will be approximate solutions that we come up with in the end, although they can be very accurate. So there are basically two main classes of methods. And the first method is, well, the first class of methods are bracketing methods. And the bisection method, which we will discuss in the next video, is an example of that. Now, how do these work? Well, what you do is you try to identify an interval between, let's say, numbers a and b, such that the 0 of the function is inside of that interval. And on this figure over here on the right, you can see, well, if a and here we have two values for xa and a value for xb. And in this case, we see that the 0 lies within that interval. As a next step, we start our iterative scheme, and we want to update a and b in order to reduce the size of the interval in which the 0 lies. And by reducing this size, well, we start closing in on the 0. So a and b are known, and we see that through iterations, we iteratively reduce the size of this interval, and we get closer and closer to this blue dot over here, which would be the actual solution, which is not known. That's not a known number, that's not a known value, but we know a and b. And as we get this interval closer and closer, smaller and smaller, then we get a better and better approximation for this solution, the blue dots. Finally, we stop if this is sufficiently accurate. This has some pros and cons, these methods. So if you can find an initial interval, these methods will always converge, and that's guaranteed. You can keep making the interval smaller and smaller and smaller, and after a while you will close in on the actual solution up until your desired accuracy. The downside is that these methods are notoriously slow. We will see examples of this in the lecture on the bisection method, but also on how the other methods can get much, much faster in finding a sufficiently accurate approximation for the solution. So a second class of methods are the open methods. And examples of open methods are the Newton method or the secant method, which we will discuss in the following lectures as well. Well, these methods, they work in a different manner. So starting from an initial guess for the solution, so an initial estimate, and how we choose such an estimate, that tends to be very important for how these methods actually converge to the solution, but more on that later. So we choose an initial estimate, and here we choose this value where the pointer is, and the function value is over here then. And then we iterate. So we try to improve this estimate using information on f, and that can be the derivative, that can be certain function evaluations of f, and that is what kind of distinguishes these different open methods from each other. Well, hopefully we start closing in on the actual solution in that case, and we again stop if the solution is sufficiently accurate. The major upside of these methods is they can be very fast. If they work, they are orders of magnitude faster than bracketing methods. For instance, Newton method has what we call, or can attain what we call, quadratic convergence. And that is, well, an extremely fast convergence to the actual solution. However, there is no guarantee that these methods actually converge. So if you choose your estimates in an unfortunate manner, it's quite possible that the method completely diverges. And also throughout the approximation of the actual solution, sometimes things go wrong and oscillations or divergence of these methods may occur. And that's something that you always have to keep in the back of your mind when working with these open methods. They can be very fast, but they're not as robust as bracketing methods. So looking at both these classes of methods against each other, well, you see that their pros and cons actually complement each other. So bracketing methods are slow, but they will always converge, whereas open methods can be very, very fast, but they might not converge to the actual solution. Also note that for both cases, well, we start from an initial guess, and then we start an iteration procedure. How this iteration procedure, so how we reduce the interval or how we use information on f for improving the guesses, well, that is what distinguishes the different methods from each other. And then there is this stopping criterion. So we stop if the solution is what we call sufficiently accurate. However, the idea of accuracy is a bit vague here, but because how do we define accuracy actually when the true solution is not known? And that is what is discussed in the next video.